A final point in this example I want to discuss is that one way to try and answer this game would be, rather than look at the average winning, look at the probability of winning, right? So somebody could say, well, if I'm more likely to win than to lose, then maybe this is a winning game. What that means, I would just look at how likely am I to get a positive payoff compared to likelihood of the negative payoff. So there are functions to determine this. We can say probability. Actually, let's first find the function and then we'll name it. So the simulation output that can help us to determine whether we're winning or not is a risk target, and this returns cumulative probability for achieving a final value, like the final payoff, less than or equal to the target. So if I click risk target, and now I select my final payoff as the first parameter, and the target value 0, notice actually 0 is never achieved. It's either $1 of loss or $1 of winning, right? And or larger or smaller than values, right? But only odd numbers are possible here in this game, right? And if I calculate this, then I see that, right, let's convert it to percentage, maybe with some, right? This gives me 42.3%. This is probability of payoff less than 0 or less than or equal 0, right? And I can also do probability of payoff greater than 0. Right? And of course, I can do 1 minus this. There is another function. However, it's called risk target D for descending, and that actually gives you the probability that the, this cell, which is our output, the payoff, is greater than 0 rather than right less than 0. Again, this is calculated based on the simulation run. So the results, these probabilities might vary depending on your simulation. I ran this for 20,000 iterations, but this is just 20,000 random sample of 20,000 games, right? So you see, it actually, we have higher likelihood of winning, right? We win almost 58% of time, something, and we only lose 42% of time. However, the problem is, of course, about the distribution of winning and losing, right? So this could indicate this is a winning game. We win more often than we lose. However, we win at most $5 and we lose as much as sometimes $73, right? The minimum payoff in this simulation is 73. And if we go to explore and see, right, okay, in fact, there are three possible results that are above 0 here that indicate winning, right? We can win 1, 3, or 5, but we can lose a large number of different right negative values. There are many here, and of course, yes, the likelihoods are very small, but even it's very unlikely losing something like $73 or other large values is enough to have one game like this to basically lose all the money you won over many of those winning games where we won small amount. So you see, you have to be careful what kind of performance measure you look at. There are many performance measures one can observe here, but the important thing is that we choose the right performance measure for the decision. In this case, because it's a repeated game, the expected or mean payoff is the right performance measure to conclude from. And if you want to have confidence about this mean, you can find confidence interval and then know that the mean payoff is somewhere in this range. And based on this, based on the fact that this range is wholly negative, then we can conclude this is a losing game.